Why is it that if I move these magnets really close together, you can feel the force between them, but when they're further apart, there's practically nothing? And if everything falls to the Earth so easily, even the astronauts, as we discovered in an earlier video, why is it that things light years away in other star systems and other galaxies aren't rushing towards the Earth as well? How can a comet and asteroid pass near us but not be attracted to us and hit us? So I have a friend called Matt. He lives in Boston. He's a great chef and he owns a breakfast place. Now in a breakfast place, one of the more annoying duties is that you have to butter a lot of toast. And because Matt's breakfast place was so small, he didn't have a large staff and he had to very often do it himself. He really got sick of spending so much time buttering toast. So, clever guy that he is, he invented something to make it easier. He calls it the butter gun. It's a gun you can hold in your hand or put on a tripod. You take a stick of butter and you load it in the back. And inside it has these heating coils that melt the butter. And once it's ready, you point the butter gun, press the trigger, and poof, the butter shoots out and covers your toast. So when he told me about this, I obviously wanted to play around with it. So I get my toast, point the gun, and poof, an entire stick of butter squelches out and hits this piece of toast. It was practically an inch thick, all pouring off the sides, really disgusting. Nobody wanted to eat this piece of toast. Now he didn't see this mess because he was busy doing other things. I was just messing around. So I try it again. I decided I need another go. So this time I get 4 pieces of toast and move it to twice the distance. I point the gun, take aim, and this time it's a little better. Last time it was an inch thick, this time it's a quarter of an inch thick. But it's still way too much, right? So then I get a grid of 9 pieces of toast and move it out to 3 times the distance. I grab the gun, take aim, and so then at 3 times the distance, instead of being a quarter of an inch thick, it was a 1/9 of an inch thick. Of course, I found out later there was a big toast rack in the back room where you can lay out all the toast, and that's how the thing works. But Matt wasn't there to tell me that at the time. So I was thinking about this, and I realized this situation has a lot in common with something in physics. The butter gun is an example of an inverse square law. An inverse square law is where something drops off proportional to 1 over the distance squared. So let's think about this. I started out at a distance d, and the butter was 1 inch thick. 1 over d squared in this case is 1 over 1 squared, which is 1 over 1. Which is just equal to 1. Then I moved it out to 2d, and the butter was a quarter of an inch thick. 1 over 2 squared is equal to 1 over 4, which is equal to a quarter. Then I moved it out to a distance 3d, and the butter was a 1/9 of an inch thick. 1 over 3 squared is equal to 1 over 9. Or in other words, with an inverse square law, if you double the distance, you decrease the quantity by a factor of 4. In this case, you decrease the thickness of butter to a quarter of what it was. There are a lot of things in nature that follow an inverse square law. For example, if you go halfway between the Earth and the Sun, you'll find that you receive 4 times the amount of energy from the Sun. If you go twice as far out as we are from the Sun, you'll find you only get a quarter of the energy from the Sun that we do at Earth. For us right now in this topic of forces, gravity is the inverse square law that we really need to know about. The force of gravity is also an inverse square law. As well as the 3 laws of motion, Newton also discovered the law of universal gravitation. Newton's universal law of gravitation says that every object in the entire universe pulls gravitationally on every other object in the entire universe. So right now, you are pulling on a galaxy millions and millions of miles away, and you're also pulling on your best friend wherever he or she lives. We see it more clearly with huge things like the planet Earth. If your mass is big enough, the gravitational force is really obvious. And gravity is an inverse square law, which means that if you double your distance from the Earth, the amount of force the Earth pulls you with goes down to a quarter of what it was. If you triple the distance between 2 objects, you decrease the gravitational force between them to a 1/9 of what it was, just like with the butter. But just to be clear, that's the distance you are away from the center of the Earth. So an object that's 2 meters high will not have half the force if you double it to 4 meters high. That's just from the surface of the Earth. You would have to double the distance it is from the center of the Earth, all the way down there. Newton's universal law of gravitation looks like this. Fg is the gravitational force between 2 objects. G is the gravitational constant of the universe, which in our universe is 6.67 times 10 to the minus 11, is always that number. M1 is the mass of one of the objects, and M2 is the mass of the other object. Last of all, d is the distance between the centers of the 2 objects. For example, the center of the Earth to the center of mass of U, somewhere in the middle of U. There are 2 main types of questions you could get on this topic. In the first, you just plug numbers into the equation. So if you wanted to calculate the force of gravity between a 4-kilogram baby and the planet Mars, you would multiply big G, which is 6.67 times 10 to the minus 11, with the mass of Mars, with the mass of the baby, and divide it by the distance between the centers of Mars and Earth squared. By far the most common mistake on these questions is forgetting the squared part. In this case, you plug the numbers in and the answer turns out to be this. Another type of question is what I'm calling an inverse square law question. It's where they make changes to a situation and ask you how that affects the force. For example, if you double the distance between two objects and double the mass of one of the objects, what will happen to the gravitational force between them? The way we're going to solve that kind of problem is by doing a before picture and an after picture. Since we're not given any numbers in this kind of question, we're going to start by calling everything 1. We're going to say we had two 1 kilogram masses and they started out being a distance of 1 meter apart. Before, we had 1 times 1 divided by 1 squared. That's just 1. We don't need to worry about big G, because big G doesn't change between the before and after picture. Big G is always the same. Now the question says double the distance and double the size of one of the masses. So that gives us 2 multiplied by 1 divided by 2 squared, which is 2 over 2 squared, which is 2 over 4, which simplifies to a half. So the force between them will decrease to a half of what it was. So there you have it. Everything in the universe attracts everything else in the universe, even a baby on the planet Mars. That force of gravity between everything works as an inverse square law, which means if you double the distance, you decrease the force by a factor of 4, not 2 as you might expect. And we can use Newton's universal law of gravitation to calculate the gravitational force between any two objects. To reinforce this knowledge, you can watch another great video on the topic by clicking here. As always, the next step is to practice. But first, let's go back to our magnets. Now unfortunately, magnets don't work quite that way. Magnetism does not follow an inverse square law. Although these ones kind of suck. So sorry for the red herring, but we'll find out more about magnetism next semester. Thanks for watching Flip Physics. Please comment below with your questions, thoughts and suggestions. If you like this video, you can press the like button. You can also subscribe or go to the flipphysics.net website. Till next time, keep questioning. Yes, I admit it. Freeze rays are a lot cooler than butterguns. Of course, Captain Hammer only needs his hammer. That's pretty much what he's all about. Butterguns are the freeze rays of Bostonian breakfast chefs.